This lesson is a conceptual overview of real numbers. Let's start with the number line. The number line contains all real numbers. There's an infinite amount of them. You often see these numbers written on the number line. These are called integers. They are non-partial numbers. Further, if you think of 1 and higher from the integers, those are natural numbers, and 0 and higher are whole numbers. Anything less are referred to as negative numbers. These classifications allow us to determine what kind of number we're dealing with. So let's look at classifying real numbers. Let's say all the real numbers on the whole number line are thrown into this box. In this box you have all of them. Now those numbers can be split into two types of numbers, ones that can be written as fractions, rational numbers, and ones that can't be written as fractions, irrational numbers. Rational numbers can be written as a fraction, irrational cannot be written as a fraction. So for example, 2/5, 3 1/3, -5, -1.25, -1.9 repeating. Those are all rational numbers. Now, when is it that decimals are possibly made into fractions? Well, it's either if they are terminating or if they're repeating. I'll let you figure out why. So if they're not terminating and not repeating, they are irrational numbers. So some examples of numbers like that are pi. Pi goes on forever and never has any pattern in it. Anything times pi, like 3 pi, will also be irrational. Also, roots of prime numbers like root 2 or root 11 will also be irrational. Now we can further classify rational numbers. These numbers, you'll notice I included -5. Even though -5 isn't a fraction, it can be written as -5/1. But you may be thinking, hey, -5 was also an integer. Why is it called a rational number? Well, rational numbers can be further classified into integers, which were the number line points, 0, 1, 2, 3, and up, -1, -2, -3, and down. Within those, we had whole numbers, which were everything from 0 onwards, and natural numbers, which was everything from 1 and onwards. You can look at these groups of numbers as sets. A set is a collection of objects, and those objects could be called elements or members of the set. Let's look at a few examples of sets. You could have a finite set of animals, like a dog, cat, and mouse. Let's go back to numbers. The natural numbers can be written like this. Those are an infinite set. You'll notice the 3 dots imply going on forever. The double-braced n implies natural numbers. Double-braced w are whole numbers, including 0. Integers can be written like this or like this. Now these sets can all have elements, and this symbol here, element of, implies, for example, we could say 2 is an element of the natural numbers, or -2 is not an element of the natural numbers. So that's a nice symbol that can be used to signify that one component is in a set. The set notation that we have been using right here is roster notation. So roster notation is where you use braces separated by commas to list out all the elements. In particular, there's a special type of set with no elements. It's called empty, and you can use one of these to signify it, but not both. Think about why you would not want to say that this is an empty set. Set builder notation is another way of writing a set. So the elements of the set are determined by a specific property, and that property is listed in the second part. So the set contains the variable such that the variable has a property. For example, the rational numbers, which are all the numbers that can be written as a fraction, can be written like the set of numbers that are written as a fraction, where those numbers are from the integers. You wouldn't want to have double fractions in there. And the bottom is not zero. So those are rational numbers signified by double braced Q. And here's another example, irrational. So you're saying all x's such that x's are not elements of the rational numbers. Negative integers, so all numbers that are in the integers set but are less than 0. So those are just some examples of specific ways of writing something in set builder notation. You can also write it in interval notation. So interval notation is used when you have, say, a long infinite number of numbers. Say everything between 2 and 5 is in my set. So I want to include 2, so I shade it in, everything all the way up to and not including 5 could be written like this, including 2 all the way up to 5 not including. So just to signify, you'd have open brackets for open circles, which imply either less than or greater than. Closed would be for including, which would imply less than or equal to or greater than or equal to. Let's look at some of the examples of this. Here's set builder notation representing everything greater than 2, but not including 2. 2 up to infinity, not including. You never want to have an including sign on infinity because there is no end at infinity. Try the next ones and see if you can get the answers. I'll quickly work through them right now. So you've got less than or equal to -2, -2 lower, everything from negative infinity up to -2, including -2, not including the infinity. Here's a between statement, greater than or equal to -1, but less than or equal to -2 or +2. Between -1 and 2, including both. Between -3 and 5, not including 5, including -3. X's such that x's are greater than or equal to -3, but less than 5. X's that are greater than 1, 1 to infinity. -6 to 7, both open. X's are between -6 and 7, not including either. Now here, you've got everything from negative infinity to infinity, which means x's such that x's are in the real numbers. You could say that. Now, there's a couple more classifications of numbers that we can look at. You can say you have inverse numbers of a set. So say you had 3, the inverse number would mean, let's say we're talking about additive inverse, that means 3 plus what is 0. The additive addition identity is 0 because 0 does not change anything when you add it. So what would you add to 3 to make it disappear? Well, you'd want a -3. So the opposite of any A is going to be -A. A reciprocal is a multiplicative inverse. So say you wanted 3 multiplied by something to get 1. Remember, in multiplication, 1 does not change anything, so that's why the identity is 1. 3 times what is 1? Well, the only way to get 3 to cancel out into a 1 would be to multiply it by its reciprocal, which is the flip. 3 times a third would be 1. And a further classification is absolute value, denoted by bars. It's used in the same step of order of operations as brackets, but it's very specific in that it represents the distance of the number in the bars from 0. So let's have our number line set up. Say we had 3. The absolute value of 3 is 3 because there's 3 spots away from 0. The absolute value of negative 5 is 5. Now, what if you had negative absolute value negative 5? Then you'd have negative 5. This negative will be still hanging out front. Some other examples, a little more complicated. You'd have to use order of operations as well. You can look at the following video on order of operations for more details. But remember, we need to do anything in the brackets first, so that gives us 2 minus 6, which is negative 4. Rest is the same. We can evaluate the absolute values. Any result, you'll notice that when you answer something from an absolute value, it always gives you a positive number, because the distance is always positive, no matter if the value inside is negative or not. So you get absolute value of negative 4 is 4 minus 7 minus 2 gives you 4 minus 7, which is negative 3, minus 2 is negative 5. Now, you can also use comparisons. So let's say we had to use one of these symbols to fill this in. So here you have negative absolute value of 0, which is 0, negative 0, which is also 0, and this is also 0. So these are actually equal. Now here, if you had the absolute value of any number compared to that number, well, all the absolute value results would be positive, and these would be anything. So these could be bigger or equal to. You can justify it. Here, you'd have 0 compared to negative x. Now let's look at this. What would this be? Negative x. Well, whatever x is, no matter if this will end up positive or negative, we don't really care, because the answer is going to be positive x. So let's just say that's absolute value of x. These numbers will always be positive, therefore will always be greater than or equal to 0. So there's a few comparisons to look at, but more specifically, let's roll back to the definition of absolute value. You've noticed that absolute value always gives you a positive number. So if you input a positive number greater than or equal to 0, the result will just be that number. But if it was originally less than 0, a negative number, you'll want to tack on an extra negative onto that expression to say that you're negating that expression in order to make it positive, because 2 negatives make a positive. So this definition, it will actually be used quite a bit in the future, so it's good to take note of right now and make sense of it.